Dear students, I welcome you all to this problem solution series in digital electronics. I am solving the problems from the book Digital Design by Maurice Mano and Michael Siletti. So in this video, I am solving the problem number 6.13 from the chapter number 6. The problem is so that a BCD ripple counter can be constructed from a 4-bit binary ripple counter. That means we have to use a 4-bit binary ripple counter and with some modification with asynchronous clear and NAND gate. That means we have to introduce a asynchronous clear input and a NAND gate that will detect the occurrence of the 1010 and it will make this 4-bit binary ripple counter a BCD ripple counter. So with a 4-bit binary ripple counter, we can count from 0 to 15. Because we have 4 bits, we can go from 0000 up to highest 1111. This 1111 means 15. Okay, that means we can count 16 number of input pulses. So for BCD counter, what we have, we can have 0 to 9. BCD means binary coded decimal. Okay, so here we have a maximum count of 9. That means from 0 to 9, we can count 10 number of input pulses from 0000 to 1001. This 1001 means 9. Okay, so whenever we get 1010, we have to reset the outputs of this binary ripple counter, okay, so that it becomes a BCD ripple counter. That means whenever we arrive at 1010, suppose this is most significant bit A4 and this is suppose A3, this is A2, this is A1. So whenever we get A4 and A2 connected to the input of a NAND gate, okay, so what we'll get at the output, will get 0. That will reset the outputs of this binary ripple counter. So here we have seen that we have input pulses here. This is a 4-bit binary ripple counter. Here we have introduced a clear input. So this clear input, this function of this clear input to reset all the outputs to 0000. So as per the question, we have to design a BCD counter. That means after 9, whenever we get a 10, it should be reset to 00. That means after getting this 9, so with the next pulse, it should go to 00. So it will count from 0000, then going up to 9. Okay, after 9, it will go to 0000. So we have used here a NAND gate. So the output of the NAND gate is connected to a clear. This clear is the asynchronous active low input. Okay, whenever it has a asynchronous active low input, it will clear all the outputs to 0000. Okay, so we have connected from A4 and A2 because up to 1001 we did not get, we are not getting any 1 and 1 both at the same time. So with the arrival of the first 1010, okay, with the arrival of this first 1010, what will happen, this output and this output are 1 and 1 because 1010, this is the MSB. Here we'll have 1010. So whenever we get at this output 1010, that means these two values are 1. Okay, so they are feedback through a NAND gate. So here we have 1 and 1. So what will happen when we have 1 and 1? The output will be 0. So here we'll have a active low input. Therefore this circuit will be reset to 0. That means after getting this 9, whenever we get a 10, that is 1010, this circuit will go back to 0000. That means this whole circuit will count from 0000 up to 1001. So this 000 means it is 0. This 1001 means 9. So it will count from 0 to 9. So it is a BCD counter. So this is the figure 6.13. This is a BCD ripple counter. Okay. Thank you for watching. If you have any question, please put it in the comment section below. Also like, share and subscribe to my channel. Thank you.